actually, so that'd be good. All right, let me wait this. This talk is based around a paper that's just appeared in Statistical Science, and that paper was joined with David Knott, Zhuzhan Yu, and then the last third or quarter or so is based on another paper where we're cutting feedback in copular models, which are inherently modular type of stochastic models. So it's really a mixture of two papers, but the bulk of it is based around this paper here. Okay. All right, so modular inference, what is it? Well, it probably hasn't passed you by that increasingly we're getting models that involve blending together different stochastic components, where you can have maybe multiple likelihood terms that you want to bolt together. And if you're a Bayesian, you join posterior inference, and you might have multiple hierarchical priors, you may have different levels, you may have a mixture of all these things. But it's increasingly common that you want to bolt together different stochastic components in your model. If you're Bayesian, you'd want to do joint posterior inference, but that gets increasingly difficult because of the size and the model misspecification issues that may arise from bolting together these components. So what is a module? Actually, module is a very difficult thing or vague thing to describe, but basically it's a collection of those stochastic terms, which often corresponds to different likelihoods, but can correspond to instead collections of priors and likelihoods together. You can be quite flexible in the way that you define a module, but the basic idea is you're sort of segmenting your stochastic model into bits, which we call modules, and one or more of them may be misspecified while the others are reasonably believable. And then the idea here is if one of them is misspecified, can we undertake some form of modified inference, and in this case Bayesian inference, that makes your results or your inference more accurate under the presence of misspecification of one or more modules? That's kind of like modular inference, particular Bayesian modular inference. To give you an idea, I'll give you a simple example that comes from a paper by Plummer, and he got that from an earlier paper as well. But it's quite good to give you a demonstration of what I mean by what currently seems quite vague. Here we've got a two-module model, okay? Two-module stochastic model, statistical model. The first is a beta binomial distribution for one source of data, and that data is a count of the number of women with high-risk human papilloma virus, HPV, in a certain age group. There aren't many observations, only 13, so it's just demonstrative. You've got a prevalence parameter phi I there that varies by observation I, by country. Then you've got a second module about cancer incidence. HPV is often thought to cause cervical cancer in women, right? So cancer incidence, and we've got some data on the number of cervical cancer cases in TI years of follow-up, and the observations are across 13 countries. And we've got a model for that that's Poisson, and the mean variance parameter mu I is specified there, and you've got this term here where you have an exponential of a to 1 plus a to 2 times the prevalence parameter for country I that came from the first module. That links these two modules up, right? The fact that phi I is in this model links these two modules up. Now, this actually beta binomial type model for the survey data, that's not bad. People believe that. It's a reasonable stochastic model. This model here, this may well be misspecified, and it's thought, but it's not easy to come up with a well-specified model. It's not like you can suddenly come up with a better version. But this is misspecified. Okay, so that's an example of a two-module case where you've got a link between the two. One module is misspecified and module one is not. So let's do a sort of graphical representation of that. There's kind of two likelihoods, two sources of data. There's the Z, which is this incidence data, and W here, which is the cancer case data. So one for HPV, one for cancer case. They have their own parameters. Parameter phi, these incidence parameters, country level incidence parameters, they affect both Z and W. whereas in eta only directly affects W. This is like a depiction. And this, obviously, this red line here is where we'd like to cut the feedback between the two. And why do you want to cut the feedback between the two? You won't want to conventional joint posterior analysis of both models together in a joint posterior, because the misspecified Poisson regression can distort inference about the prevalence parameter phi, or phi's, because there's 13 of them, right? It's a vector of 13. And that happens when you undertake conventional joint posterior analysis. So you want to make it more robust. That means if that happens, that means that the slope of the prevalence, which is eta 2, will lose its interpretation. Because basically eta 2 is the most important parameter in that pair of models, right? You want to see how much does HPV prevalence transfer into cases of cancer. Okay, so eta 2 tells you that. If eta is 2 to 0, then it doesn't happen. And so it quantifies that. So that's something you want to do. So the idea here is, do we have some modified Bayesian analysis which doesn't use the conventional joint posterior that can improve upon that case of using the conventional joint posterior? That's what multi-modular statistical models are all about. And in the Bayesian case, you want to be able to create valid posterior inference for parameters in those correctly specified modules. So, for example, we want to have accurate posterior inference about the eta, the phi i's in that model, the prevalence parameters. In doing so, that helps you interpret the parameters in the misspecified models. If the prevalence parameters phi i's are well estimated, then you can interpret the eta 2 parameter. If they're poorly estimated, then eta 2 also loses interpretation. That's one thing to do with the inference. The second thing is that if you cut feedback and reduce the impact of the misspecified model parameters on the correctly specified model parameters, can you also improve prediction? And we have some demonstrations, indeed it does. Okay, so there's a bunch of work on this. We're not the only people, but the prediction question, there's a paper by Carminer and Nichols that has a look at that. And the paper I'm going to talk about in the last quarter of the talk, that also talks a bit about prediction. So there are a number of ways of doing this modular inference. I mean, it's not just one way. There's a number of ways of doing the modular inference, but the way we're focusing on is this idea of cutting feedback. And it was originally built as a Bayesian analog of two-stage estimation. I don't know if you know these models, but there's these pharmacokinetic and pharmacodynamic models. This is where it all began, really. Pharmacokinetic models kind of model the diffusion of a drug in the bloodstream. They're very accurate. That's something you can build a good stochastic model for. All right, and you don't have many questions about model misspecification of the pharmacokinetic component. But pharmacodynamic relates the drug concentration to some physiological outcome. And you just imagine that's a lot harder to specify, and it's very hard to build a stochastic model that's reliable for the pharmacodynamic modeling. And if you do joint posterior analysis on both, you end up messing up the parameter estimates in the well-specified pharmacokinetic model. Consequently, a two-stage analysis where you estimate the pharmacokinetic first, then plug in parameter estimates as if they're exact, and then estimate the pharmacodynamic model is obviously attractive. It's just simple two-stage estimation using any inference method, right? But in our case, we want to do that, but also propagate uncertainty about the estimates of the parameters in the pharmacokinetic model. So it's about propagating uncertainty as well as cutting feedback at the same time. Now, how do you think of cutting feedback? There's a number of, it's actually quite a difficult thing to define a cut posterior, but one way to do it, and this is the way people did it for a long time, is think of it as an implicitly specified entity by modifying a Gibbs sampling scheme. So, and that's implemented in WinBugs and OpenBugs with this function cut. If you think of standard Gibbs sampling, of course, you take your parameter vector, which also includes latent variables, where else you want to chuck in hyperparameters. Theta, you partition it up and you generate for one block conditional on the others, right? This is what you do, and you generate from the exact conditional posteriors repeatedly, and it converges. That's good. Cutting feedback can be undertaken by taking one or more of those conditional distributions and deleting or modifying terms in the conditional, and then running the MCMC with the modification. That defines a cut posterior implicitly. You haven't got a closed form for it in that case, right? You've just got an algorithm, and its stationary distribution is the cut posterior. So that's the way people thought of cutting feedback for a while. Let's think about what that means for this sort of two-module system, very much like the HPV and cancer example. What does it mean? Well, let's think about what are the two posteriors here. Here's the Gibbs sampling scheme, right? You generate the incidence prevalence parameters from their conditional. You generate the coefficients of the Poisson model from their conditional posterior. These are all specified up here. These sort of simplifications come from the fact that you've got this structure, right? That the likelihood of the data, which is Z and W together, can be factored in this fashion, right? This is the joint likelihood of Z and W together. Okay, and when you look at the posterior of eta, you can sort of drop this term because there's no eta in it, right? So you get this very simple decomposition for those two conditional posteriors. When you cut feedback, what you say is, well, if I'm going to do it through the MCMC scheme, I'll just cut out this additional term here, P of W. Okay, so I cross it out, and then there's no feedback, right, from the eta parameter to where your draws of phi are. So that cuts feedback, but you're still propagating uncertainty by doing a joint MCMC scheme. Okay. In the case of a two-module system, you have the advantage that you can write down the joint cut posterior analytically. And that's what the final line on that slide is doing. That's not true when you have multiple modules, like 3, 4, 5, 6. It's much harder to write down an analytical expression for the cut posterior. But here, the cut posterior with this adjustment is simply given by this expansion here, right? Which is this density times P of phi given Z. Okay, by composition. All right, so that's the joint cut posterior with a simple modification. If you want to compare the two, right, you can see something, right? So there's the cut posterior, joint posterior for phi and eta together, and here's the conventional posterior. You can call it conventional, you can call it uncut, same thing. And you can see the only difference really is that the marginal posterior distribution for the phi there is conditional only on Z in the cut, but in the conventional posterior, it's conditional on Z and W, Y being Z and W together. Okay, but you can see cutting the second module has no influence on inference about phi. But there's uncertainty propagation about phi when making inference about eta. Think about it. If you use this thing here, if you want inference for eta, you have to integrate over phi. It doesn't disappear. Okay, so you want the marginal posterior of eta from this term here, you've got to integrate over phi. So the uncertainty propagation about phi is achieved. So that's that. And that would not be the case, of course, in just two-stage plug-in type methods, right? Okay, so as I said, the Gibbs sampling approach in two-module systems, and that's one type of two-module systems, but it's true in general with most two-module systems, you can get an explicit characterization of these cut posteriors. Now, as I said, when you have more modules, it's much more complex. We're really going to focus more on the two-module case, which is huge. Okay, oh yes, sorry. Go ahead, shoot away.
Hi. I just wanted to ask a question about the previous slide.
Sorry, we can't hear you. Do we have a mic here? Or?
The rest of the people on the call can hear FX, so it's likely your sound.
No, it's on. Oh, hang on. No, the volume's on.
Can you hear me now? Hello? Okay.
Tell you what, how about we keep the questions to the end, not because I don't like answering questions go along. In fact, I love answering questions as they go along, but because the IT thing is not working at the moment. Oh, the chat? Oh, yes, so it is. Mike's. All right, okay, we'll leave it to the end because I got quite a bit to go through, but I was intending to do it with 10 minutes at the end, so I wasn't going to fill it all up with talk, okay? All right, now, even in the two-module case, think of a case where phi and eta are actually very high dimensional, and maybe the likelihoods for W and Z are more complex than Gaussians, right? So they're quite complex stochastic models. If you write down the cut posterior for that two-module case, first of all, you got this term here, which of course just writes down of P as Z given phi and its prior. And then for this conditional posterior here, you use Bayes' theorem, and you have your usual numerator, and then you have what normally when you do Bayes' theorem is the marginal likelihood, but you're conditioning on phi, so it's the marginal likelihood given phi. That term there is usually intractable as the models get more complex. So even though you can write down in a two-module case the cut posterior in this analytical form, the denominator of this term here is very difficult to evaluate. Okay, so that's an intractable term for many realistic two-module problems. In that case, working with the cut posterior as an entity in itself is tricky. Another problem that's arisen is that when you use these Gibbs sampling algorithms, if you can't modify Gibbs sampling algorithms, if you can't generate directly from one of those conditional distributions, you don't have the usual recourse of using Metropolis Hastings. If you do, it's a very interesting observation that you can see in the paper by Plummer. If you do, the resulting sampler or the stationary distribution of the resulting sampler depends upon the proposal that you use. Why is that? That's because the modified Gibbs steps that you've created by deleting or modifying components of are not the full conditional distributions of the target cut posterior. Consequently, if you use detail balance to get your acceptance rate, accept-reject rate of the Metropolis Hastings scheme, it's not a proper generation mechanism for the target cut posterior. So that's something I must admit, I didn't think that up, and I didn't believe it until David pointed me towards that. Now, there's a lot of previous work on trying to compute cut posteriors, and probably the most common one is this one. Plummer gives you a few, and the most common one is to use sort of nested MCMC schemes with an MCMC scheme within it, an MCMC scheme. You can just imagine that doesn't scale, which I'm sure you're aware. So existing methods, all of them are computationally intensive, and some of them don't target the correct cut posterior anyway. You can't guarantee it. So that makes you think about how else you might do that. And one of the natural things you might think of, it turns out to be very well adjusted for this problem, is variational inference. And that's what this paper is mainly all about, suggesting variational inference methods to evaluate these cut posteriors, which are notoriously difficult to evaluate. Now, there's some other work on using variational inference for cut posteriors. Kimona and Nichols has a paper as well that was concurrent work. I direct you to look at that if you're interested in variational inference as well. But I'll talk about what we've done. Now, if you know something about variational inference, it's probably the second most popular form of Bayesian inference method out there. The first one being, a collection of MCMC schemes for exact posterior inference. Variational inference, the idea is that you do approximate inference. The idea is you're trying to approximate the posterior distribution. Now, that posterior can be like an augmented posterior, latent variables and other things, but you're trying to approximate a posterior distribution, P of theta given Y, with another density called Q that is tractable. Simpler and tractable, and people usually pick things like Gaussians and other things for that. And the idea is that that Q has to come from a family F of densities. And if you solve this, it's called the variational optimization. If you solve that problem, then you have an approximation to posterior Q star, and then you can do whatever inference from that you reach, right? Work out its mean, simulate from it, work out tails, whatever. And we do it by minimizing the kubelet-Leibler divergence. And one of the reasons they use the kubelet-Leibler divergence, or this method really comes from machine learning more than other ways, is that maximization, the minimization problem, where you minimize the cubic line, the divergence between the posterior and its approximation, making them close in a density sense, is equivalent to maximizing this elbow function. It's like you solve one, you solve the other. It's a very simple derivation that you maximize the elbow function. And the great thing about the elbow function is it looks like this, and you think, well, that looks a bit complex, but really it's an expectation. So it's weighted by Q theta there. This is just an expectation of this term here with respect to Q. And that expectation is really easy to deal with because it's an expectation with respect to a tractable density Q that you choose. So you can evaluate the expectation using a variety of methods, Monte Carlo methods more often than not. But there's a suite of well-accepted and sexy methods for doing those expectations, right? Now, most people will use, use what's called mean field approximations. That doesn't work so well in a lot of circumstances, as we'll see. And the other one is fixed form, which is what we suggest mainly in this paper. Let me talk about mean field first. So mean field approximations, I've got in the box here, that's where that approximation Q is can be expressed as a product of densities on a partition of the theta. So if you take the theta vector and then you partition it in some way with k blocks, mean field, that approximation is a product over the densities of those blocks. Okay. And then let's say we can take the Bayesian posterior, right, and then factorize it in terms of these fj's. Each fj is just a term that involves collections of the partition elements of the theta. So let's say you can sort of separate it that way. It may be one element in that theta partition, or it may be a collection of them, right? It's a bit awkward notation actually for that, but that's the idea. You can sort of separate it out into separate blocks. That the posterior can be separated in separate terms that are dependent on subsets of the partition of the parameter space. Okay, now why do I do that? Because one way of doing mean field variational inference on the cut posterior is to adjust an algorithm that's quite popular called variational message passing. There's a nice paper on JASA by Matt One, but there are other papers on this topic. And they observe, and obviously not go through the details as a paper in itself, that the optimal QI star that solves the variational optimization, maximizing the, minimizing cubic line divergence or maximizing the elbow function, that's the variational optimization. The QI star that solves the variational optimization can be written as proportional to what's called these messages from factors in the decomposition of the posterior to individual parameter blocks. Okay, the algorithm is an optimization algorithm that's called coordinate ascent variational inference, or CAVI. So that's something that's used, but it can only be used for those mean field variational approximations. It's no use for any other family of variational approximations. So in our paper, one thing we look at is we do the same trick that people do with Gibbs sampling. In Gibbs sampling, as I said, to evaluate a cut posterior, they take a Gibbs sampler, take one of the conditionals and drop off a few terms or modify a few terms, and then run the sampler until you just get a result, and that's the cut posterior implicitly. Well, you can do the same with modifying variational inference message passing algorithms. You go to the CAVI algorithm and you drop message components that are analogous. And then you run the CAVI algorithm, and that gives you a variational inference estimate of the cut posterior. Okay, that's one way of dealing with this problem. Now, let me show you what that does with a really, the same two-module example, just with some simulated data. So we've got a Z and a W as before. Let's say you've only got a small amount of data for the Z. Let's say N1 is small, you get some data, and let's just say it's generated from a simple normal distribution with an unknown parameter, which is this location phi. That's what you kind of want to estimate, or one of the parameters you want to estimate. Let's say that's not much data, so you have some additional information or additional data that is similar, but it's biased. So that data is W, and Wi there is from a normal with phi as its mean, but it's got a bias parameter eta. All right, now they've both got a standard deviation of 1 for simplicity, right? So eta is the bias parameter, and this is not an unusual thing where you have some reliable data and there's not much of it, and you have some unreliable data and there's lots of it, right? So that's the idea, hence the bias. we believe the bias is small. So because of that, we build priors that reflect our model. As Bayesians, our priors reflect our beliefs. And eta in particular, we give it a normal distribution with a large precision, or equivalently a prior variance that is small. Same thing. Okay. Now, we're still using this cut model, and we're going to work out cut posteriors for that and conventional posteriors and see what happens. Let's simulate some data. So there's 100 observations from the first component, 1,000 from the second. Eta is truly 0, but phi is truly 0. The true mean is 0, but eta, your bias offset, is 1. Now that bias actually turns out to be in the tail of its prior. So our model for the W was misspecified through the prior being wrong. It was too tight. Okay, so we've got this model here. This model here is misspecified actually through the choice of the prior for its parameter. It's too tight. What does that do to the conventional posterior? Well, here's the outcome. What I've got is density plots for eta, and phi. Okay, let's look at these orange or reddy sort of lines here. First of all, that dashed one there, that's the exact posterior for eta. The exact conventional posterior for eta. That's just using MCMC. So you can work them out analytically in this simple example, of course, which is what we do. And eta here, the exact conventional or full posterior here for eta. Both of them are just wrong, right? They're away from the true parameter, which is the black line there. Okay, so bad estimates in terms of point estimates and distribution. The blue there is the variational approximation to the conventional posterior. Located well, variance is tight, right? The other ones are the cuts. These are cut posteriors. Let's look at this one. This is the exact cut posterior, and this is the variational cut posterior using the variational mean field approximation that I mentioned, right? They both get the location pretty well. Variational is tight. Similar story over here. Oh, by the way, they're on top of each other here. In this case, they're exact, which is why it's missing. That's usually in the caption underneath, right? So first thing. What happens when you look at the bivariate case, or bivariate posterior eta and phi? The variation, you can see sort of like, this is the mean field approximation. It just gives you these sort of independence between eta and phi. And that's not true, because that's the true posterior up there. This is both for the exact and also the cut posterior. Small combinations: cut, exact, variational, cut, conventional, variational, full. And you get all 4 combinations of those 2 words, right? So mean field, it is quite known actually that mean field variational approximations can underestimate the posterior variance quite chronically. Consequently, people try to widen the family F of variational approximations so that you make less of a problem in estimating the posterior variance of a parameter. And that's what we're going to do here. We're going to use what's called fixed form, which are just distributional choices for the family F. They're going to be parametric. There are non-parametric families as well, but we'll just talk about the parametric ways. We're just going to use actually a normal distribution, but not independent across the parameters like the mean field. Okay, and you'll find that it does a lot better job straight away. Same simple model, it keeps coming up. It's always good to remind you of what we're trying to do. We have a result in the paper. So the paper really, this is the guts of it in terms of its innovation. If you have an approximation Q, approximating density Q for phi and eta to its posterior distribution, and we'll define Q subscript phi as its marginal in phi. It's the marginal variational approximation in phi. Then if you define the following family of densities, F cut, what they are is densities, bivariate densities in phi, or multivariate densities in phi and eta. This is true whether phi and eta are scalars or vectors, right? So it could be quite high dimensional. If you have a joint distribution over phi and eta here, such that the marginal in phi is equal to the cut posterior marginal, all right? That's the cut posterior marginal we had before from some of the earlier slides. If you remember, you drop the y and replace it with a z. in the 2-module case that we had depicted. Then we have this Thoroughling theorem. The density in the family of approximating densities f cut, defined in this way, that is the best approximation to the full posterior density in the Kullback-Leibler sense, is given by our joint cut posterior. What does that mean in practice? What it means is that you only have to solve once you assume this cut family, that family f cut, as your space of variational approximations, then you only have to solve a regular variational inference problem to get the cut posterior. Regular variational inference problems are easy to solve. Okay, so what you've done is you've pushed the complexity of evaluating a cut posterior into narrowing the family over which you optimize over. And then the variational optimization problem is a regular one, which is simple to do. And in particular, we have this algorithm in the paper. What you do is, first of all, because you don't know what the marginal cut posterior is, this thing you want to constrain the margin of Q theta to be, what you can do, first of all, is choose a form for Q. A multivariate normal, mean mu, variance covariance matrix, capital sigma. Could be quite big, right? Then what you do is that you optimize the parameters of the Gaussian margin in phi. And let's say lambda there represents the means and variance components of the marginal Gaussian distribution in phi. So you optimize that first. You're solving a standard regular variation inference problem to work out an approximation to the cut posterior margin. That approximation to the cut posterior margin is Q lambda star. It's going to be a normal, if you pick a normal. Then, to get the approximation to the other parameters, eta, what you do is that you define your space of family to be Q, as before, this bivariate Q, but such that Q factors to the marginal that you've already worked out times this conditional. All right, which will just, it's a Gaussian, right? So this is Gaussian as well. And then you solve a regular variational approximation problem in lambda tilde. The advantage of doing that is that you don't have to work out that troublesome denominator term that we had before. Do you remember we had that marginal likelihood that was conditional on phi? That was and it was intractable. That was the bottleneck. This variational algorithm avoids having to ever evaluate that. So it becomes a soluble problem. And using regular variational inference methods, which are very fast and very simple, sort of thing you could put a couple of third-year classes on, no problem. They're just stochastic gradient descent, okay, with Gaussian approximations. Okay, go back, this is the model. We're going to go back and have a look at what happens here. Here's, for that data, what I've done here, I mean, I probably should have plotted contours, but we generated from the models, right, the posteriors. What I've got here is variational posteriors on the left, exact posteriors on the right. I've got the full in blue, that's the conventional posterior that's uncut. And then I've got the cut over here in this mesh, this sort of orangey reddy color, right? Burnt orange or something, okay? And you can see that if you evaluate them exactly, you see the cut makes a lot of difference. Here, what I've got on the horizontal axis are eta 1 and eta 2. So these are the parameters of the cancer module, module 2, right? Eta 1 and eta 2 there. I mean, I could show you the posterior of the 13 estimates of the prevalence parameters, phi 1 up to phi 13, but I'm not. I'm just showing you these things. Notice that eta 2 is the really important parameter in this joint model. And you can see that cutting feedback makes a big difference. And the variational approximations are really accurate too. Okay, they're not exact, they are approximate posteriors, but they're pretty good, right? They're lined up very well. Okay, all right, that's good. I've got 10 to 15 minutes to do the next part. So I promised you some newish work, at least I promised Jim I'd do something that's new. So this has just appeared on Archive, which makes it exciting to me, but it doesn't mean it's exciting to you. This is joint work with David Nott as well, but also David Brazier from Monash and another U, actually. This is Wei Chin U, so that's a different U than in the statistical science paper, which was Su Chin. One of the things we noticed, of course, is that you can think of copula models, something that I've sadly spent too much time on, as modular constructions as well, right? Because you have a copula and then you choose marginals. It's one way to build a multivariate distribution. So a copula model is a modular construction by its very nature to begin with. You can use that to improve inference on it. Rather than using the joint posterior for a copula model, you can use cut posteriors, as we'll see. And that paper is all about that, both theory and practice. So if you know nothing about copula models, all it is a decomposition for a multivariate vector yi. Let's say y is a multivariate vector with m elements, and they're all continuous valued in this case. Okay, then you decompose its joint density into this factor here. It's a copula density where its arguments are the marginal CDFs of the data, usually called the probably integral transform values if you're an econometrician. And then it has some parameters here, phi, and I'm deliberately using the same sort of notation as before, which are the dependence parameters of the copula. This could be a Vine, it could be Gaussian copula, it could be T copula, it could be anything, right? And then this is a product of the marginal densities Fj. These aren't messages anymore. Marginal densities Fj of the copula. Okay, I'll pick up an independence prior here, but you don't have to. All this flows through without the assumption of independence priors, by the way. Just make it simple. So we're going to treat that copula model as a two-module system. And in particular, module 1 will be the copula, module 2 will be the collective choice of margins. You could break it up into a two-module system in another way. You could say copula plus some margins, and then the other marginals. It's up to you. But here we'll just do marginals and copula. And we'll think about cutting feedback, right? And the first way we cut feedback is from phi to eta. And this corresponds to the following case, where the copula density may be misspecified, but the marginals are not. When you build a copula model, by the way, in practice, it's almost impossible to well specify every component. You're either in this case or case 2 that I'm going to look at in a bit in a while. So how would I cut feedback? Here, it's relatively easy. So I'm going to just go through a few lines. The marginal of eta given y, what is it? Well, that's the product over n is just like n observations from the copula model, right? So that's all we've got independently made. It's just that likelihood times the prior. The prior for eta is on the outside. And of course, you marginalize out phi, right, to get the margin in eta. We plug in our expression for the copula, for the joint density of yi from that copula model. There it is. How do you cut feedback? Well, you cut out the red terms, right? So if you include those terms without the crosses through them, that's the conventional marginal posterior of eta. Now I cross out the red terms and I'm modifying feedback. Notice if I do that, there are no more phi's in that expression. And the integral over phi is just 1. So I cut out every term that involves phi, basically. All right, and then if you do that, you get the marginal, if you go through one or more lines, you get the marginal posteriors for each marginal set of parameters, just using the data from that marginal, which is the y subscript brackets j. Okay, that's collectively you can call that the cut marginal. Then you can put that together with the conditional for phi given eta, and you have the joint cut posterior. And that does the uncertainty propagation. By putting those two together, you do the uncertainty propagation. That's actually a Bayesian analog to inference for margins, which is a well-known technique in frequentist estimation of copula models, but it allows for Bayesian uncertainty propagation. So it's a pretty straightforward. A more complex case is the other form of cutting, where instead of cutting from phi to eta, you go the other way around. You cut from eta to phi. That corresponds to the alternative form of misspecification, where your marginals may be misspecified, but your copula is not. So you do it the other way around. That's a more difficult and involved form of cutting. What we do in the paper is we propose to replace the copula density that you saw in the box for the copula model before. We replace it with something called the rank likelihood. That's the likelihood associated with the ranks of the raw data. That doesn't have any marginal parameters eta in it. So by replacing, rather than deleting terms, replacing that C term here with the rank likelihood associated with the rank likelihood for the ranks. This term here, instead of being deleted, is replaced with the rank likelihood term, but it doesn't involve the etas like this term does, right? So you can cut feedback. So we replace it, and then you can work out P of phi given Y, the copular parameters. Well, they're just proportional to the rank likelihood. It still has the dependence parameters of the copula, by the way. Still, rank likelihood use the copular function, but not the marginal arguments, basically. And then you have the prior for phi. Again, we use the same trick through composition. Two module systems are easy to define the joint cut posterior because you have this construction, right? Where you do a cut marginal, you derive that, and then you multiply the conditional, and then you get uncertainty propagation go through to the joint. We're totally unaware of any analogous estimator there. There's certainly a lot of non-parametric estimators in copular modeling, but there is no analogous estimator for this. So this is just like new. Now, I've got 5 minutes, which is really good. I've managed to time this quite well. So it gives us 10 minutes for questions, which hopefully we can get working. You can evaluate those cut posteriors for this copular model when m equals 2 exactly. It's computationally intensive, but you can do. But as m gets larger, you cannot. And by larger, I mean like 3 or 4, you're gone. All right. So, but when m is large, like greater than 2, that variational inference algorithm that I put up with the fixed form approximation works really well, like up to thousands, m equals thousands. It really works well. So for the case 2, where you use the rank likelihood, I haven't got into the details there. That's much more tricky because when you impose the rank likelihood is actually quite intractable in itself. The way you make it tractable in a Bayesian sense is you add some latent variables, and then the extended rank likelihood is tractable. Even in variational inference is tractable. So if you have an extended rank likelihood with some extra latent variables, when you combine that with the priors, that's called the augmented cut posterior, right, in this case. So there's, in the paper, there's a fair bit of discussion about that, and that works quite well. In the paper, we also look at a lot of theory. Where fortunately, we had David Frazier, who is strong in this area. And we had a look at the theory of it, and among a number of other things we established, you can show that there's asymptotically correct calibration of the cut posterior under the appropriate form of misspecification. So if you use case 1, case 2, it matches up with the form of misspecification there is, or if the model is correctly specified. So you are, if the model is correctly specified, you can use the conventional posterior or either cut posterior. They're all asymptotically correctly calibrated. But if you have one of the 2 types of possible misspecification, you want to be using the appropriate cut posterior. And we show that empirically as well as theoretically. Now, one thing I want to show you, because in the last few minutes, we have a substantive example there. We have a paper, sort of update on an earlier paper of mine where I did some copular multivariate time series modeling and forecasting. We had 4 macroeconomic variables observed over a lot of periods of time. We used a Gaussian copular process. If you do that, it actually produces a large Gaussian copular model with dimension 1096. So this is a large Gaussian copular model. It's not, the copular parameter matrix is not completely free. It's actually derived from an underlying 72 unique parameters because it's a copular process. Okay, so you can do that. We have 4 skew T marginals, 1 for each of the macroeconomic variables. It's likely in this model that either the marginals or the copular, or both actually, are misspecified. But one of them is quite gross, as we will discover. We evaluate those cut posteriors using variational inference. We can evaluate the conventional posteriors using the Smith and Vey algorithms in that paper, and that's MCMC. And we can judge accuracy by out-of-sample predictive log scores. So my last slide here is this. There's a lot of output for that from that analysis, but this is something I just want to show you. For each of the 4 variables that we have, GDP growth, inflation, interest rate, and unemployment rate, what I've got plotted here, first of all, I got plotted based on out-of-sample forecasts, 1 step, 2 steps, up to 8 steps ahead. What I've done is I've got marginal predictive densities from the cut posterior, case 1, cut posterior, case 2, and the uncut or conventional posterior value using MCMC. And what I've done is I've evaluated the accuracy of those 1 to 8 step ahead predictions. And they're density predictions, right? I'm predicting the whole density, okay? The whole predictive density. And we have a measure of the accuracy of the predictive density. There's a variety of them. This is the log score. You could use the cumulative rank probability score or some other metric, that's fine. This is a density forecasting metric of accuracy, the log score. Higher values are good, all right? And you can see here, black is kind of the Smith and Vey approach for inference. It's the same model, but this is the Smith and Vey approach for inference, conventional posterior. And you can see that's dominated particularly by the red. In practice, that's a big difference when you look at the density forecasts, particularly in the tails, which are really important here. So the red is case 2. What was case 2? Case 2 was when the marginals were misspecified, but the copula was not. So the actual copula is not so bad. It's the Gaussian copula. It's actually the marginals. And that's not surprising given what's happened since the 2016 paper. We updated the data and we've got the pandemic in there. And then we have like spikes at 0 inflation rates and growth that goes off to -10% and stuff like that, right? So the skewed T marginals are inappropriate. But you don't really have a better choice. That's the problem. Okay, and it has to be parametric because you want to do dead tail probability evaluations for extreme outcomes. All right, now that's my time up. That's good because I've got here's a few of the papers. Some of them, yeah. I'll point out one. So this is the paper that I talked about in the last 10 minutes. Okay. So other than that, now can we get the volume up because I think Francois Xavier wants to ask a question.
Maybe if there's any questions in the room for Mike, then maybe Mike can answer those, and then I'll try and work out how to use the volumes.
All right, shoot away.
Yeah, so I guess when you're looking at the variation inference and the setup that you do, where you first look at the margin or phi and then do the second stage. So are you still doing a mean fields approximation by it?
No. So the approximation is for the joint. But you think about Gaussian, the simplest case, right? You have a multivariate Gaussian for everything as the variational approximation. Its margin is Gaussian. You calibrate those elements first, and then you calibrate the elements of the conditional, which are the sort of blocks on the off diagonal plus the other parameters in the, I'm thinking about the covariance matrix of the Gaussian. You calibrate them next in the second stage of the variational optimization algorithm. So it is a joint distribution for all parameters in the model, both modules, but you calibrate one subset of variational parameters first, and then you calibrate the second set, holding those constant. You solve a joint variational optimization problem with some of the variational parameters held constant.
So this first one that you do, the first parameters, is that still the components of that parameter are going to be independent or not?
No. So the variational approximation Q, this family here, this is what first of all is I work out those variational parameters lambda star.
So that can have correlation between components.
Yeah, so this thing here, this has correlation between the components of phi and eta involved in it as well, right?
So
we just use the conditional of a Gaussian.
So what's the advantage of doing it this way over more flexible joint Gaussian families in the posterior?
Well, in this case, the advantage of this algorithm, regardless of what you choose for Q, whether it's Gaussian or more flexible family, is that you avoid calculating this tricky normalizing constant that I'm cycling at the bottom. That is intractable in general.
So it's a computation.
Yeah, I mean, this is literally, it doesn't matter how fast your computer is. This will become intractable. In the Gaussian copula target model that I was talking about at the end, that you could never work out this term.
Right, okay. This is basically why you can do it.
Yeah. Yeah, so variational approximations here are not just a way to speed up the computation. They actually solve the intractable nature of evaluating the cut posterior. So that's qualitatively different, right? And to be fair, Komonos and Nichols also observed it as well.
Okay, So, wait a minute, Kadina.
Chat.
For people online, they're going to have to type in the chat. There's no way I can turn on the speakers. They're kind of locked off. So sorry about that. But if you want to ask a question, please type away, and that will give Kadina a time to ask her question.
Thank you. So I have a question about the mean field approximations, but I need to set up the stage for my question.
Okay.
Please bear with me. So in the term mean field approximation comes from physics, from large physical systems. So there, when you blow your system with many particles to infinity, you are going to end up with the mean field with independence statement, and it comes from definity. Yeah. So the way you can prove it mathematically is by definity. So what they do in physics, or even for example in Schrödinger equation, what they do. So you don't have the mean field. Of course, there is no independence in the real world, but you can subtract the mean field in some sense, and then you can divide by an appropriate parameter which depends on the number of elements in your system. And then you're going to end up with a term which is quite good. It's not mean field, so it's sort of a next order term, and it's pretty good. And you can even subtract that term, and you end up with the next order term, and that makes, and then you can write all these terms one after the other, and you end up with something which is pretty nice. And you can do that even for many electron Schrödinger equation, which is a double variational formula. So first you fix the marginal, and you try to look at the first variational formula of a fixed marginal, and then you remove and you take another variational formula over that, in which you look over all the marginals, and things can be quite nice.
So,
do you have anything like that? I mean,
no. So here, that's just nomenclature that's been inherited in the machine learning literature, but it's very interesting. We just use mean field to say, well, we assume independence between components of our approximating density, and then we calibrate it. And in practice, it's actually quite good at getting locations, but of course, it's horrific at getting higher order moments of the joint posterior distribution that you're trying, or the target distribution you're interested in. But yeah, it's the history of how these words got inherited. It's kind of interesting, right? No, but I knew it was from computational physics. I just,
But I mean, do you have anything? Can you use the mean field in some sense in the way that in physics they can?
No. They just in this form of literature, it's just a word they use to describe assumptions of independence of length.
You have your product measure there. It appears in your mean field approximation. You have a product measure, so that's why can you somehow use it and subtract something in some sense? And because once you subtract the product measure, you no longer have independence. You're going to end up with quite a heavily correlated system. So it's just a tool in the physics. It's just a tool. You remove it, and then you end up with something which is heavily correlated, and you keep the dependent structure in the system once you subtract the mean field, and you go to the next order term which has the dependent structure, and the more next order terms you remove, the more you get, the closer you're going to get to the two structure of your system. So.
Yeah, no, I'm not aware of it. I just inherit the term, but I have no doubt, there's a great deal of depth to this, far beyond what I know.
So this is a bit less about the variation one, it's more about the color in general. I guess another way to think about inference in this misspecified scenario is to kind of generalize posteriors, right? One fairly simple approach to this is whether it's kind of same phase where they kind of temper the likelihood. And it kind of feels a little bit like the cut approach is tempering the contribution right down to zero.
Yeah, no, so the alternative approach here is semi-modular inference, which is very similar to that. So what they do is that they cut partially. So there's a parameter that controls the amount of cutting you do in a continuous sense between 0 and 1. And that's called semi-modular inference. Yeah, I mean, that's another way to think about the problem. There are clearly, like in the copular model case, it's pretty clear in that last example that cutting is better than not cutting. it would be an interesting question of whether partially cutting would improve further still, or whether it would be redundant. I don't know the answer to that question. It's
I think thought about as well looking at concentration type results.
yeah, so that's the semi-modular inference, and you know, Carmona and Nichols look at that, but also, you know, David Fraser's done a fair amount of theory on it recently. He's also, people tried to do cut likelihood-free inference as well. So that's a kind of an interesting topic. What does it even mean, right? Well, they give you some specification of it. But, you know, in practice, this is only something that's going to get bigger, because the tendency in the physical, medical, and social sciences increasingly is to bolt together different models, and they get bigger and bigger, and the data sources multiply. And there's value in doing that in terms of improving predictions, but also improving causation understanding as well. So, you know, they're already like that in social sciences with simultaneous equation model type stuff that people look at. So cutting could do a lot to improve inference when some of those modules are kind of not that accurate, and other modules you believe a lot. The drug stuff is really important, right? You really can define an excellent diffusion of drug through the bloodstream with a few unknown parameters, but the model is really well specified. But linking that to actual physiological outcomes on how you feel, you can just imagine the model for that will always be much worse specified. So the cut posterior will always be an improvement. Man.
Thanks, it's really interesting. Yeah, I had a follow-up question, an idea from about this idea of putting, you know, disparate data together. I wonder if can you see some of this as a bit like the idea of a commensurate prior approach, where you might see, you know, the data source that you're not so sure about, you kind of think of it as feeding into because it looks a bit like that, doesn't it, when you get your cut posterior, so that the data source you don't believe so much is almost acting like a prior for the bit you want.
Yeah, that's exactly right. So in the paper, we have David Knott has written a sequence of papers on prior posterior test statistics, and you can treat one module source of data as the prior, and then augment it with a second set of data and update it in a Bayesian sense to a posterior, and then compare the two. And that's one way to judge whether it's effective to cut or not. So we actually use exactly that idea to derive a test statistic for whether you should be cutting the posterior or not. So actually, that's exactly right in the two module case.
Oh, so only in two modules. So
yeah, well, in the multiple module case, it's much harder, right? You don't have the sequencing in the same way, where you can pick one and then followed by the other.
Okay, so I think we're going to have to draw a line there.
Okay.
So maybe you can answer FX question by email.
Okay. Yeah.
No, that's okay. So sorry about that, FX. It's been a bit of a disaster for you. But,
we cut you out.
Mike will be happy to email you an answer to your question. So thanks to Mike again.
Thank you for inviting me.
No, we overran. That's our problem.
Apologies.